Good morning, good evening and good night. Depending on which time we are going to observe this lecture. Welcome to the 7th lecture on solution chapter. In this lecture, we will be going to discuss a very important topic. This has in reference to our lecture number 5. In the lecture number 5, we have discussed about the vapor pressure in the solution where both the components are volatile components. By using the Raoult's law, we can have one equation. From this equation, we can able to calculate the vapor pressure of the solution containing the volatile components. And this equation is, we know, that is some P is the vapor pressure of the solution. Vapor pressure of the solution, that is equal to the vapor pressure of the pure component 1, that is represented by P10X and its mole fraction in the solution, and the vapor pressure of the second component, that is the component 2, and its mole fraction is X2. From this you can able to determine the vapor pressure of the solution which is having both the components are volatile. Now in this lecture we are going to discuss again a very important thing, that is when one of the component will be non-volatile. And this type of solution you can able to see in your day-to-day activities. Suppose we are adding sodium chloride in water, or glucose in water, or cane sugar in water, or urea in water. At that time, this type of solution that is one portion of the solution, that is basically you can see the solute is the solid and solvent is the liquid, and it is the volatile substance. So in this lecture we are going to discuss what will be the vapor pressure for those solutions which is having one component is the non-volatile and other component is the volatile. And after this we will going to discuss what will be the impact on the properties of the solutions of these solutions that we are going to discuss in this lecture. Okay, so heading of this today's lecture we can write that number 1, we can discuss that vapor pressure. Vp is basically vapor pressure of the solution, vapor pressure of solution containing one non-volatile substance, non-volatile component, and it is basically the solute, And second thing, the properties of the solutions, this type of solution. Two things that we are going to discuss in this lecture. So this is K. Mukherjee in the Science with Mukherjee Sir YouTube channel. So first let us understand, this is the first part of this lecture, that is the vapor pressure of the solution which is having one component is non-volatile and other component is volatile. We can easily understand the vapor will be created by the volatile substance. Suppose the component 1, we can write the component 1 is component 1. Component 1 is volatile, right? And component 2 of the solution, component 2 of the solution is non-volatile. Okay, so this component will create the vapor, but this component will not responsible for any type of vapors in the above the solutions. So we can modify this equation, that is we are giving here Ps is equal to P10 into x1, P20 into x2, and this component now is not going to contribute anything towards the vapor pressure. So we can omit this component. So vapor pressure of the solutions which is having one component is non-volatile and other is volatile is having a vapor pressure is this. And from this equation you can be able to understand that vapor pressure of the solution will be less than the vapor pressure of the pure component 1. Vapor pressure of the pure component 1, that is being designated. This is basically the P10. We can write the vapor pressure of pure component 1. Pure component 1. So this is the vapor pressure of the pure component 1, and we can easily understand this will be vapor pressure will be less than P10. So we can understand from this discussion that it is a very important conclusion that has been drawn, that for these solutions where we add a one component is non-volatile, at that time the vapor pressure of the solution will be less than the vapor pressure of the pure solvent, that we can easily able to understand. So for this solution we can see the vapor pressure will be always lower than the vapor pressure of the pure component, and this reduction in the vapor pressure of the solution, which can be correlated with the different types of properties of the solution. Properties of the solutions, like number 1 that we are going to discuss, that is the relative lowering. This is the property that is going to be changed. Properties of the solution that is going to be changed, that is relative lowering of vapor pressure of solvent. Number 1. Number 2, this reduction in the vapor pressure of the solution, which leads to the depression or we can say lowering of freezing point, of the solvent, or we can say of the solution, solvent or solutions. Number 3, the elevation means increase, or we can say increase of the boiling point. We can increase of boiling point. Third, fourth, that is the osmotic pressure of the solution. So we can understand this reduction in the vapor pressure when we add some non-volatile substance to the solution. It leads to the change in the properties of the solution, or you can say solvent. In this thing, number 1, that is the relative lowering of the vapor pressure. Second, the depression of the freezing point of the solvent. Third, it is the elevation of the boiling point. Fourth, that is the osmotic pressure. These are the four important properties of the solution that has been affected by this reduction of the vapor pressure of the solution when we add a non-volatile substance. Now question arises why there is a reduction in the vapor pressure. We can understand it in the physically. Number one, that is suppose the container. In this container, that is a closed container, in the container you can see when there is no non-volatile solute. At that time, the surface of the liquid, it is covered with the solvent molecules only, when there is no non-volatile substance. But when the non-volatile substance has been put, at that time you can see some of the portion of the area, surface area of the solution will be occupied. Suppose this is a non-volatile substance. This will be occupied by this non-volatile substance. Naturally, the vapor pressure is created, the area from where the vapor pressure is created by the volatile substance will be reduces, and when it is reduces, it is going to reduce the vapor pressure in the above the solutions, because number of the particles, number of the molecules that is in the upper surface of the solution is now reduced and it is replaced by the solute molecules. Solute molecules will not going to contribute anything towards the vapor pressure because it is non-volatile, and at the same time we are reducing the number of molecules which has been replaced by the solute molecules, and that is going to less number of the solvent particles will be evaporated. So there will be the lesser vapor pressure. We can understand here number of molecules will be less due to this fact there is a lesser number of molecules present in the surface of the solutions. That is, the molecules of the solvent will be lesser now because this is replaced by the solute molecules, and that is why you can see the solvent pressure of the solution will be less than the vapor pressure of the pure solvent. That is the explanation behind this fact. So these things has been analyzed and it is found that there is the four properties, the important properties of the solutions is going to be affected with this reduction in the vapor pressure. And these properties that will be it depends on, we can write, it depends, these properties all are, it depends on the size, depends on the number of, depends on the number of the particles, number of the particles present, not on the nature, not on the nature of the particles. We can write this very important thing. It is depends on the number of particles present, not on the nature. Means suppose we add glucose, 1 mole of glucose, we add 1 mole of urea, we add 1 mole of other non-volatile substance. This effect will be same. It will not depend on the nature, whether it is glucose or it is urea or it is cane sugar. It will not going to be affected. But its number of particles. In 1 mole, we know number of particles will be same, so it will going to be affected in equally. So it depends on the number of the particles present, not on the nature, and this is called the colligative property. This is called, we can write another very important thing, that is, it is colligative property. So we understand, when we add some non-volatile substance to the volatile substance and creating a solution, at that time the vapor pressure will be reduces and it will be less than the vapor pressure of the pure solvent. And this reduction in the vapor pressure will going to influence on different properties of the solutions. That is, we have already understand, that is the relative lowering of the vapor pressure. Number 2, the depression or the freezing point. Number 3, the elevation of the boiling points. And number 4, that is the osmotic pressures. All those properties will be. So the 4 properties that is being affected by the reduction in the vapor pressure of the solution when the non-volatile substance has been added to it. That the first is the relative lowering of the vapor pressure. We can write the relative lowering of vapor pressure. Relative lowering of vapor pressure. That we are going to discuss. So already you understand from the previous discussions, that is the vapor pressure. PS is vapor pressure of solution. We can understand it is basically, we can write P10, that is the vapor pressure of the volatile component 1, that is P10 will be represented, and X1 is mole fractions. So we can write this equation in this way: PS by P10 is equal to X1. X1 is the mole fraction of the solvent. Suppose in the solution there is a mole of the solvent present is N1 and total mole is N1 plus N2. Here N2 is the mole fraction of the solute. So you can write here also, for clarity, you can write that N1 is basically the moles of solvent, and N2 is basically the moles of solute. So this is X1 is mole fraction of component 1. Component 1 here is the volatile component, and X2 is the mole fraction of the component 2, which is non-volatile. This non-volatile. So we can write this. Now we can further simplify this. We have to express this expression as the relative lowering of the vapor pressure, that is -1 PS by P10, that is 1 minus N1 plus N1 plus N2 is equal to P10 minus PS by P10, and that is, you can see, it will be N2 by N1 plus N2, and it is basically the X2, the mole fraction of the solute. So these terms we can say this is the relative lowering of the vapor pressure. This is relative lowering of vapor pressure. Lowering of vapor pressure. Vp is vapor pressure. So from this, Raoult proposed one very important law for the non-volatile solute. This is called the Raoult's law of non-volatile solutes. Raoult's law of non-volatile solute. What it says? It says the relative lowering. You can write this relative lowering of vapor pressure. Relative lowering of vapor pressure of solution. Vapor pressure of the solution containing non-volatile substance, non-volatile component or substance, whatever it may be, component is equal to the mole fraction. Very important thing, mole fraction, equal to the mole fraction. Here it is the X2 of the solute present in the solution. That is the Raoult's law for non-volatile solute. It says the relative lowering of the vapor pressure is equal to the mole fraction of the solute present in the solutions. So this can be further written that what is the utility of this law? Let us understand. Suppose we want to know the molar mass of any component for any substance. Suppose we want to know. That can be easily, indirectly can be able to calculate with this experiment. Suppose we put this volatile substance in the solutions in the water, suppose volatile substance, and at that time we measure the lowering of the vapor pressure of the solutions. The vapor pressure of the solution naturally will be lower, and how much it is lower, that can be calculated from this. This is called the relative lowering of the vapor pressure, and from this we can able to calculate the molar mass. How we can able to calculate the molar mass? Let us understand from these solutions. So this we understand the relative lowering. Yes, by this. Now suppose the solution is dilute solution. In this dilute solutions, what will be there? This N2 will be much less than N1. So at that time we can write N2 by N1. Suppose there is a W2. W2 is the mass of the solute, and its molar mass is M2, suppose, and W1 is the mass of solvent, and M1 is the mass of molar mass of the solvent, suppose, molar mass of the solvent. So we can put this here, W2 by M2 divided by W1 by M1. So we can write this W2 into M1 divided by M2 into W1. So from these relations, that is, you can see relative lowerings will be equal to this expression, and in this expression you can see you have to know this amount of the solute has been deposited and molar mass of the solute, right? And if you know molar mass of the solute is this, suppose solute is this, and molar mass of the solvent is this, and molar mass of the solvent is this. If you know this, we can able to calculate this M2. So from this relative lowering of the vapor pressure, we can able to calculate the molar mass of the solute. This is how we can exploit these things, right? So this is all for the today's lecture. In this lecture, we have discussed about the very important thing, that is the when we add some non-volatile substance to the volatile substance, the vapor pressure of the solution will be decreases, and if it decreases, it will going to affect many other properties of the solutions. One of them is the relative lowering of the vapor pressure, that we have discussed, and how these are going to influence the molar mass, how we are going to influence, and how we can able to calculate the molar mass of this, that we can able to understand from this lecture. So that is all for today's lecture. The next lecture we will discuss another more important that is colligative property, that is the elevation of the boiling point, difference of the freezing point, and the osmotic pressures. Thank you very much for watching. Thank you.